Thank you, Ilya. Good morning. In Turkish, günaydın. So I lied. I know a few things in Turkish. I hope everyone had a fantastic night, being exhausted from the first panel session, all that, right? Day 2, I'm exhausted too. But I hope everyone's doing well. So today, day 2. Today, we will continue with our virtual topologies. Yesterday, we did Cartesian graphs. And then today, we'll touch on, I go to the next slide, you'll see it, graph topologies. So we're going to start connecting some really fun unstructured things. And then we will do neighborhood collectives, fairly short. And then finally, we'll do some mesh partitioning with metis. So try to go through that. So we'll see. I'll try to take my time. I will give lots of time. I think there are technically 3 hands-on exercises. We'll probably get to 1 at the end of this session on the distributed graphs themselves. And then the second one, we'll do neighborhood collectives, which is pretty short, right into another hands-on exercise. And then we'll touch on metis, and then you guys can play with a piece of a C code that I wrote with that reads an unstructured triangle mesh with an airfoil, which is fun, and passes into, and it links to metis and partitions, and then you can look at the visualization. It's a unstructured VTK format, if you know what those are. And then later this week, there's a visualization tutorial in one of the parallel tracks if you're interested to see how you can load it into ParaView, for example. But we'll take a look at it today. So maybe ahead of time, while we get started, we're going to be back on Bridges 2. So in the interim, while we get going, make sure you can log back into Bridges 2. And then in the exercises, again, there's a script, right? Interact 8-day 2. It's one of those bash scripts. So run that, so that way you can already get your 8 cores, and then we'll be ready to go in the hands-on exercises. So, any questions? If we end up racing out of time, we'll go back and review all of kind of yesterday's exercises and today's and much more review. Yes? Okay. I think we'll move on. We'll get to today's lectures, have some fun with some nice graphs. Okay. There we go. Okay, graph topologies. So here's a wonderful graph where we have a bunch of nodes. And then what we have here, so these nodes represent MPI rank IDs again, right? So we've already had some imaginary graph, and we've mapped it to these MPI ranks. But then we have these numbers here, these connections. And with these connections, you can actually give a weight. So for example, I know rank 0 and rank 3 is going to have, this, 1,983 units of communication. So within these topologies that we can build, we can actually embed this information. And then we'll see later about the actual reordering, like remapping of the rank orders. It'll take this into account, okay? At the same time, if you don't provide this, which you don't have to, provide these integer weights, it should recognize, depending on implementation again, how many connections, because you can have redundant connections between your nodes, in a sense, or your rank IDs. And then if it's clever, it'll reorder. So I think I derived, you'll see in the hands-on exercise, we'll basically have 4 nodes, and then only 2 of them will communicate. So it'll be like 2 groups with redundant connections, and hopefully it'll reorder so it'll actually detect that. I don't know. I think I tried on Bridges and it should work, so hopefully. But if you Google reordering for this stuff, you'll actually find people complaining about Intel's MPI, and I think they've resolved that issue. So it's kind of fun. But Okay, so here's our wonderful graph, right? So we're getting into much more complicated or sophisticated data structures, right? Which don't lay into that traditional, Cartesian connection, right? Where you have a regular pattern of who I'm going to talk to, right? So here you can see, right? So there's a connection between 0 and 3 on the left, but then you can have like skip connections and redundant connections, right? So in MPI, there are 3 ways we can make graph topologies. The first one is called graph create. Second one is distributed graph create. And then lastly is a special case, dist graph create adjacent, okay? But it's really, the second one in the middle is the most generic. And we'll see each one of these, okay? So the first one, graph create, is suppose this is our graph. What happens in graph create, they came up with this probably in like MPI 1. And what happens is we construct this graph, so we have to set the nodes and all the edges, we have to explicitly write them out. But there's a copy of the entire graph on every single rank, okay? So how do we create a graph topology? One way, right? So here is that function call. Today, I tried to eliminate all explanations of all the input parameters, but just give you emphasis on the important ones here. So, right, we're going to pass in our old communicator, right, like com world. We're going to pass in how many nodes there are in our graph, and then we have this index and edges arrays. We can pass in our reorder int flag, right? And then finally get out our communicator. So if you didn't notice, right, so far, kind of, what do these do? Well, they make a communicator that have endowed information like embedded into the structure of an MPI com type, right? And so you can actually query against your communicators like, hey, are you a special communicator, such as a Cartesian com, or are you a graph com? So it's kind of interesting under the hood, right? They're storing stuff inside of this MPI com type, okay? But for index and edges, right? So let me just skip over to the example to explain indexes and edges. So this is a simple graph. It basically has every single scenario. You have nodes that have outgoing, so 0 only communicates out to 1 and 2, right? So the error is going out. We see 2 talking to 1. 4 is all by its lump sum, doesn't talk to anyone. And then we have 2 bidirectional, 1 and 3. And then actually 5 can talk to itself. Okay. That's yes, every scenario, right? So how many nodes do we have? Well, we have 0 through 5, so we have 6, right? And so what you want to do in order to figure out these indexes and edges is one trick is to make this table. So first we're going to make this top right table where we start with MPI process 0, okay? And then we're going to say, okay, 0 is connected to which nodes? Connected to 1 and 2. So we say because it's connected to 2 other nodes, it has a degree of 2, okay? And then you'll have on the far right a accumulation tally of the degree. So you'll actually see this as kind of what's called a scan operation. We're going to accumulate from all the previous ranks up and store it in the right. So rank 1, how many nodes is it connected to? Well, we can see 1 is connected to or talking to 3, right? Node 3 has degree 1, so going connected right out. And then again, we take 2 plus 1 is 3. Okay, rank 2. On the bottom left, we see it communicates out to 1, degree 1, accumulation 4, right? Pretty straightforward, right? You'll see these. 4, fun, doesn't talk to anyone, and it has degree 0, so our tally is still 5. So we have 6 nodes, right, when we have to make this communicator. And then so the indexes, it turns out, is just really this accumulated degree set of information on the far right, okay? And then edges indicate basically our actual nodes we're connected to, okay? So remember, on index, on the first one, it said we're connected to 2 nodes inside of our indexes array, right? So 2. And then what we do, if we map it, we look, there's going to be 2 entries of the node IDs that rank 0 is connected to, right? So because there's 2, we're going to see 1, 2, and they're connected to IDs 1 and 2. Okay, next, we have accumulation of 3. So the difference, right, from 3 minus 2 is back to 1. So that says on node 1, we should be talking to node 3. You guys see how this is kind of stepping? Yes? Exactly. So this is compressed storage row scheme, CSR. There's also an, what's the other one? Column, right? CSC or CC. But you're exactly right. So this is a technique that we use for compressed row storage, if you guys have heard of that. So suppose you have a matrix that is massive in terms of its dimensions, million by million, but it's sparse, meaning a majority of the entries of the matrix are actually 0. So on a computer, you don't actually want to store all of those 0 entries. So a way to do that is kind of this technique, which is called CSR or CRS, compressed row storage or compressed storage row schemes. And we'll see when we get to the Metis example, this is exactly what we need to do. So this kind of scan technique, right? So we build this accumulation degree, and then on the bottom, it basically tells us how big are the units, and then who do they talk to, okay? Lots of fun transitions again today. Okay, and then simply, I placed it here for continuity, right? And this is the graph create, passing in nodes, indexes, edges, and reorder, and we get out our fun new communicator. Now, imagine a graph with 100 billion edges. You work at a social media giant, unnamed, and you are mining everyone's social connections. And there's a lot more than 100 billion edges, for example, right? So if you were to tally up and look at how much memory, it would take around a terabyte per MPI rank in order to store this using this technique, because there's a copy of this graph, the entire graph on every single rank. So that's pretty poor, and so it's not scalable, right? So we totally advise in real life, in practice, do not use graph create. But of course, your hands-on exercise, we'll use graph create. Actually, it's this graph. I had a bad example. I got rid of it. So good. Okay, the new technique, the better way to do this, right? This is the most generic way to make a graph communicator, and it's called disgraph create. So it's a distributed communicator. Okay. So here's our wonderful graph again, right? 0, 1, 2, 3, with these select connections. And so with disgraph, what we do is each process, MPI rank in a sense, is going to construct a part of the graph, okay? So that way, when we assemble under the hood through MPI, it'll know the entire structure, but we're only storing a part, okay? So on the first one, we could store, 0 and 2, that link. On process 2, we could store the 0, 3. And then we skipped over process 2, and there's nothing there, but it's fine. There could be stuff there. And then finally, 3 can have multiple connections, right, to complete the graph. So, right. Now, the interesting thing here is, as you notice, right, node 2, or process, right, MPI process 2, has nothing. But there is actually, right, you can see on MPI process 0, there is rank 2 is involved. So it's fine. There's no actual relationship that is needed in order to construct the graph. So in theory, you could use like rank 0 to connect the whole thing, and then all the other ranks would know about it. But of course, that's bad. Yes? Because you can do whatever you want. That's the beauty of this function. So it doesn't matter. I just arbitrarily picked weird random connections. Okay. So it's just recognizing like when we want to distribute the actual construction of the graph, and so we could just kind of, yes, you're right. As you'll see in adjacent, which is the third one, we actually map like, okay, node 3 should be responsible for like its own connections, right, to its adjacents. But in this one, it's super generic, so you're free to do whatever and whoever connects it up, okay? Just to give you that extreme flexibility. That way there's no like corner cases where like, well, MPI's got to add another one, right? Okay, here's the fun little function call. Again, so this is a little bit more generic, right? So we have to give nodes, sources, where is information coming from, because now it's directed edges, right? It's degrees, we'll see, destinations, and you can assume, you can now give it weights. How important are these communications? Okay, yeah, and as on the bottom, a little caveat, process ID has nothing to do with actual node IDs. Okay, let's look at process 0, and I'm just mapping here actual, being intuitive, right? I'm gonna take process 0 and actually think I'm gonna map it here for convenience, right? So here, how many source nodes, I better look at this. Yeah, okay. So how many source nodes does 0 have? Well, it has 2. Let me see here. What did I do? Did I botch this? Does this make sense? Hold on. Like sleep deprived like everyone else, right? Apologies. I'm trying to interpret what I was constructing. So let's see here. Oh, source nodes. Ah, yes. Okay. So if we look at node 0, it has, let's see here, 2 sources, 0 and 1 degrees. Right, the construction. Yes, I believe that's correct. Right, right. So, yes. Yes, thank you. Right, okay. So what is sources? Oh, this is a rough morning already, huh? So sources, right? On the distributed graph, we're going to pick the nodes that were, how many are we going to store on this graph itself, right? We say, okay, we're going to store 2 nodes that'll act as sources. And then on the sources, we have to say how many connections they have, right? And then for like, so the sources is actually the node ID. So we're going to store 0 and 1, right? And then for the degrees, we look at node 0. There we go. It's all coming back to me now. And then we say, okay, node 0 is connected to 2, right? So there's 2 directed edges. And then here we have to store, right? 2 plus 1 is 3. And so the 2 corresponds to the nodes you're actually connected to, right? So destinations, 3 and 1. Correct, but yes. So remember, this is really flexible. So we don't actually have to store all the information relevant for the entire node, okay? So I think I do another on process 1. We'll see it, right? So we didn't actually store this connection, right? This last one, it's not there. But we have to have some other rank build that connection in for us, right? But because it's completely flexible. Oop. right? So the other ranks will construct the other ones. Yes. Mm-hmm. From here? Okay. So on process 0, we just randomly said we're going to store 2 nodes. We could have picked, we say, okay, on process 0, we could have had process 0 construct the connections for rank 3, for example, and 5. We could have just arbitrarily picked, okay? So why I confused myself this morning at 8 or 9 a.m., whatever time it is, right? So we picked, okay, 0 is going to be responsible for nodes 0 and 1 in part, right? And so it's going to say, all right, I know where the source nodes are. And then we say, okay, how many of the edges do you want to store on each one of those, right? And so we said, okay, on node 0, we're going to make 2 edges that we're going to learn. And then we're also on node 1, we're going to store 1 of the edge connections. But we could have picked 2, right? We could have also done that, but we didn't. And then here, right, and then we say, okay, we're going to have 2. So then we have to list out the actual node IDs we're going to talk to for those, right, for those connections. Right. So the main benefit is that the information in order to construct the whole graph is distributed. So on node 0, we only have a subset of the information in terms of memory, right? So that way we're not duplicating memory, and it's distributed in the sense. So basically it just all comes down to the amount of memory that you're not using. That's simple, okay? But this one is like completely flexible and confusing, as you can already see. Yes? Yes, excellent. Correct. Yes, that's it. Thank you. Thank you. Yes. Yeah, I believe so, yeah. Correct. Number of processes as well. We should be careful with that, right? So we kind of use those terms in. Right. So you're correct. We have this notional sense of like you're responsible for that process's nodes, right? So yes. So in the example where you had node 0 could have 10 million edges, and we can't store, all of those edges on that one. So as we'll see in adjacent, the next one, we would have to say, okay, node 0 has to create all of the 10 billion edges, but we would blow up memory. So then we'd have to fall back on the most flexible one, and then let other ranks build the connections in for node 0 and distributed, right? Even though I may not have anything to do with those connections, right? It's purely for memory, right? In order to distribute the graph and how everything is stored, right? Hopefully it's balanced in a sense, if it's a really big problem. Mm-hmm.
So if you're doing this, and you had, again, node 0 is 10 billion connections.
Yes.
And you had you put that on 5 more, let's say, 5 more processes.
Mm-hmm.
And you did reorder. And you're doing
Yep.
this on a big cluster.
Yep.
With the reordering, then put all of those on the same rack. Appearing, because I assume that you need a lot of communication between the ones that have edges and the ones that.
Yes, but here's a caveat. When you ask it to reorder, all it does is say, hey, I think it's a smart idea. Here's a new rank ID that you should have. But once you get this new rank ID reordering, it's actually your responsibility or your decision to use it. And if you had data related to say, okay, in the old COM world, rank 0, get mapped to rank 10 in our new graph communicator. And if that was in a different location, right, then we'd actually have to ship any associated data ourselves to that new one. Okay, right? So it's our still responsibility. We just get like a hint. So do we have more questions? I know we had a few. Yeah. Yeah. 0. Yeah, I believe so. I'd have to look at the standard again. So out of all these, right, when we're like learning these functions and stuff, you just look at the MPI standard, right? And then you see what is the actual, correct procedure, but I believe it's a collective. Is that right? Where everyone's calling it, even if you have 0? So so John Kaz on the spot, if you have a rank that is not involved in the construction of any of the edges, does it need to call graph create? Yeah, see, that's why we have the MPI standard to tell us the answers. So, okay, we can look. Yes. Oh yeah. So I think you can give it hints. I have to look at the I have to look at the standard again to see, like, you can pass in like extra information, and like it's a another thing, kind of like ComWorld, where there's endowed information that you can access to learn about the graph itself. I believe they update stuff. Yeah, I refer you to the standard. Okay. 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 So any process, best flexibility, most confusion. But so because we built this in a way where it could be completely arbitrary in the construction, right? So we had a MPI rank that had nothing to do with another process, and we're registering nodes. In order to actually give everyone, a full bird's eye view of the graph, this requires a global communication, right? So that can be expensive in order for these, to inform everyone else what's going on, right? So most flexibility, right? But slightly more expensive. So let's look at the actual logical one, as you guys have already alluded to, which is adjacent. So same graph, but now each MPI process is actually responsible for its edges, and solely those edges. So local information only, which is great. Directed edges, and then what happens though is we have redundancy in the sense where if there's a connection, then you can have a node, an edge listed twice. So there's kind of redundant information being stored in this thing. Okay, so MPI process 0 has connections to 2, 3, and 1. So obviously we're going to build those 3 connections, right? 1, most logical, right? It's connected to 0, 3. 2 is connected to 0, and 3 is connected to 1 and 0, right? That actually makes sense. It's easy to explain. Okay, our fun function, again, right? So now we have a bunch of input parameters, in degree sources, weights for the sources, out degrees, destinations, and weights associated with the destination edges, right? Yep. Okay, so process 0, which is mapped to node 0, logically, right? Because that's how this works. And so the in degree of node 0, it has no edges coming into it, right? Do we have to have that? So in the second one, in degree kind of specifies the sizes of source and source weights. So are we going to have any source or source weights? Well, no, right? Because there's no connection. So we can actually skip over that one. So skipping to out degree, there's 2 connections going out. And where do they connect to? They connect to nodes 3 and 1, right? Makes sense. Okay, process 1, again, so we see in degrees 3, then we list out all those nodes that connect to, out degree 2, and we list all those destination nodes, right? Makes total sense. Okay, and then everyone else is responsible for constructing their own. Same story. Okay, so again, review. We looked at the bad one, the do not use in practice. Then we looked at the graph create, which is confusing, but it's most generic. And now we know why and a good reason why you might need it. Thank you, awesome students. And then lastly, the adjacent, which we just saw. Okay, now, yes, question. one-to-one, say that again, one-to-one mapping between the edges and nodes? Yes. Yeah. And right, so if I go back a little bit, quick. See, in the yellow there, each MPI process specifies all edges in which is part of, and solely those edges. So that's why it's one-to-one mapping. It wasn't, right. So this one, I guess in mathematical terms, is bijection mappings, right? Okay, let's get me all the back. The problem when you put in too many transitions, it just takes forever to get everywhere. Okay, mapping basics, right? So we kind of alluded to the rank reordering stuff. And why might we want to do that? We want to help reduce, congestion in the communication patterns, right? But it does depend on if the MPI vendor, whoever's supplying the MPI implementation, actually takes advantage of the stuff, okay? So here's an example of our awesome graph again from the very beginning. And so the naive mapping might be, right, 0, 1, 2, 3, 4, 5, 6, 7, right, where we just lay it out because this was the original COM world rank IDs, right? So we said, okay, rank 0 and rank 1, you should be on the node, right? So we're going to store those here. Now, what I did here is I constructed so node 0 can hold 2 ranks, for example, if we're in like a tiny little cluster. And then, so for each one, right? Now, if we look at the connections themselves, we see we basically ignore how much the communication is between 0 and 1. So I'm just ignoring, even though they don't communicate, they're there, okay? So if I'm going to send information, for example, from 0 to 3, I have to go through, let's see here, I have to go through 1, over to 2, through 3, okay? Now, because these are node mappings, and what we do is we look at the actual accumulated communication path, right? So if I want to talk from, let's see here, 0 to, let's do 1 to 4, okay? Did I do that right? I probably screwed up the math again. So, but anyways, what's happening is we're seeing a lot of congestion, right, between these nodes. So if you carefully look at this graph, you can actually accumulate the weights between them two and get the sum between, right? And we have very expensive stuff, and we have connections that don't make sense. And if you use reorder, in theory, it can recognize that we can reduce the communication loads in between nodes. So maybe the smart way is, we see in the original graph that 0 actually talks to 3 the most between those two nodes. So they should probably live on, or between those two ranks, they should probably live together on a node in order to reduce the latency of the communication, right? And then next, right, they kind of make logical sense, right? So 5 and 6 has a pretty heavy load of like 3,667 in terms of its weight, right? And so if you look at the other connections, is there any other connections between the rank IDs that are more expensive with say, rank 5? Well, rank 5 is connected to 0, and it's only 2,200 versus 3,600, right? Or if you look at rank 6, it only communicates with 2 and 0, but it's in the hundreds. So it makes sense that the reordering should put the most communication pairs together in this example. Okay. All right. So there's a couple query functions which are useful once you. Yes. Sorry. Yes. So let me give you an example in my awesome or fun CFD stuff, right? It's kind of like a Cartesian grid almost, right? With adaptive mesh refinement. But it could turn out that the neighbors themselves, right, between elements that obviously have to communicate, right? And within each one of those elements, I have variable amounts of data, right? And so it could be that I have to communicate much more frequently with my neighbors, of course, right? And so with the weights, right, I can indicate to MPI, right, the implementation that, hey, can you reorder it to make sense to put these two ranks close together, right, in order to reduce that communication latency and improve performance, right? Okay, so we can ask on this graph, we'll pass in our brand new distributed graph, and we can tell it to spit out, okay, once I have it on my rank, how many ranks are talking to me? How many ranks am I talking to, right? That's the out degree. And if you decided to specify weights associated with those connections, then you can get those weights back out. It's basically querying the graph. Okay, so, right, in degree, out degree, and these are the sizes, okay, of each one of those. And why would you need those? Well, on the next call, as you'll see, we'll actually pass in, we'll use that information to allocate memory in order to access, okay, who is actually talking to me? Or who am I actually talking to? And so that's what we see in the bottom in terms of these arrays, like sources, right? So that would be related to in degree. The other interesting thing is, so max in degree and max out degree, is suppose you have, again, a crazy example where you had rank 0 talking to 10 billion other nodes. But when I query, I don't want to actually learn who I talk to, right? I don't want to blow up memory. So you can actually limit how much information you want to get out of this query. So you can say, hey, only give me the first 10 ranks that I'm getting information from. And then in sources, this will be of size 10. And then it's going to provide me the first 10 ranks or nodes that I'm actually getting information from. Does it make sense? Yeah. I think it's based on the way you constructed it, right? So when we passed in, when we are creating that graph, that ordering gets embedded. So how you constructed it is how you're going to get it back. Yeah. That's a very good question. Well, so recall, so reorder, right, just reorders the rank IDs, right? But we can still query the global graph, right? So all the connections still there. Now, how it assembles between, right, like, that's a good question. I don't know how that ordering works, but it's probably from like logical, like rank ID, but I don't know how the reordered one, if it's from the new one, right, new rank ID and stacking it that way, or if it's from the old one. Yeah. Oh, yeah. So remember, in the top here, we're going to get the actual counts of how many we actually have connected to. So in degree is just a single integer that's going to get assigned how many total connections there are. So we know what the totals are. And then if we wanted to do batches, we would limit max in degree to be less than the total in degree. And then we can keep track ourselves of who we've talked to or learned, right? Okay. So in this example, if we look at node 1, right, we see that the in degree, right, shown in purple, we're talking to 3 nodes. So in degree would be 3. And then we could say, okay, if we put in a max in degree of 3, then our source array would tell us, if we registered it that way, it would say we talk to nodes 0, 2, and 4, for example. And then at the same time, we can query how many nodes is rank 1 talking to, and it's talking to 2, right, shown in red. And then we would get the list of destinations if we put the ordering in as like 3, 4 when we construct it. Okay, pretty straightforward. Okay, finally, hands on. We'll get you guys woken up. And I will, torture you with some C programming with probably bugs in it again. So, okay. Let me pull up the other. Okay, again, logging back into Bridges. You guys should already have your nodes, hopefully. You already have your exercises, so you don't have to run this again. But right away, if you didn't run Interactive 8 day 2, right, just run that once, leave it on. You'll see under, right, when you log in, make sure you're not running on login nodes. I saw that quite common yesterday, right? So bad practice to be running MPI jobs on login nodes. So make sure when your name, it should say like, my username is on like RM34 or something, right? To indicate it's a node. If you see -login, you know you're on a login node and you shouldn't run these scripts, right? Because it's bad practice. Yeah, I was at a university which they should have known better, but they're running like full-on machine learning workloads on head login nodes, like for like 48 hours straight. And I was like, stop doing that. And I'm like, oh, why not? I was like, because. Yes. Good learning. Okay. How are we doing on time? Okay. Good. Good at killing time. So I'll give you guys where are we? Oh, yeah, we already did those. Oh my word. Okay. So here under exercises 3, right, you'll see this C code. And we made this little contrived graph, right? See in the upper left, where we're only going to have 4 ranks, right? And we're going to use that most generic one to construct this. But it makes sense. I didn't mess with you too much here, right? So between the ranks, we have double connections that are bidirectional. So you can redundantly put in communications, right? So we have 0 talking to 2, and we have 1 talking to 3. Now, the reason why this is a contrived example is if you are on like 2 nodes, for example, the logical ordering would say stick 0 and 1 together on a node, and we would stick 2 and 3 on a node together. But they don't actually communicate at all. So in this example, you'll actually set reorder to 1 and see if bridges does the right thing. It tells you a new rank ID, right? So I think your job will be to actually construct the distributed graph. So here you can see that process 0 is going to be responsible for constructing between 0 and 2 the outgoing communications. Okay, on rank 1, it's going to be responsible for the outgoing communication edges from 0 to 3. On 2, it's going to do the reverse, right? So 2 talking to 0, and 3 talking to 1. So because this is the most flexible one, did we actually satisfactorily cover, if that was the right word, did we actually cover the entire graph across all the MPI ranks? Do we have all the edges? Do we have all the connections? Yes, no, maybe so. That's the question you're going to be asking yourself, right? So it's good to have this mental map up front. And then you guys will build these connections, which is the fun part. Okay? Okay, so 20 minutes. And then, as I had already alluded to, did the ranks get reordered? Okay. Your time starts now.